Hi everyone, my name is Brandon, and I'll be presenting my work about differential verification of deep neural networks. This is work that I did in collaboration with my lab mate Jingbo and my advisor Chao, and we're all from the University of Southern California. So by now we probably all know that neural networks have achieved state-of-the-art performance in many important tasks. There's image classification, speech recognition, and autonomous driving, just to name a few. But neural networks can be surprisingly unreliable. A very well-known example of this are adversarial inputs, where seemingly insignificant changes to an input can cause a drastically different output from the network. And this unreliability is a huge cause for concern when they're used in safety-critical systems. So by now, there's many works to improve reliability of deep neural networks. We've seen software engineering techniques used, like testing and verification, to improve the reliability. However, many of these techniques are just focused on a single network. This is a problem, though, because many of the properties we might want to consider are properties of two neural networks. For example, after the initial training, we might apply some type of compression technique, or we might retrain the network with some new data later on. And in these cases, we have an original network and an updated network. So this naturally raises the question of, does the updated network faithfully mimic the original? So current state-of-the-art cannot tackle this question, and it's an important question to answer because we often expect the updated network to be functionally equivalent to the original. For example, in the case of compression, we expect the neural network to perform identically to the original. So this brings me to our contribution. We designed and built a tool called ReluDiff that is the first differential verification technique for neural networks. And in particular, ReluDiff can prove the equivalence of two networks within a small error bound, which we call epsilon. And to give a comparison point, we adapted a few state-of-the-art single network verification tools to our problem domain. And compared to these tools, ReluDiff can verify hundreds of properties that these tools simply can't handle. And when both tools finish, ReluDiff is often up to 3 orders of magnitude faster. Okay, so for the remainder of the talk, I'll give an overview of ReluDiff, and then I'll touch on our evaluation. So we'll start with the overview. So first I'll define what a neural network is. A neural network can be thought of as a mathematical function that takes as input real numbers and outputs real numbers. And it computes its output by taking its inputs and performing a series of affine transformations, followed by performing an activation function. In our case, we focus on the ReLU activation, which takes its input and outputs the max of 0 and its input. So now we can define the problem we're interested in. Given two neural networks, f and f prime, and an interval for each of the inputs to the network that describes the input space that we're interested in, we aim to prove that the difference between f and f prime is bounded by epsilon for any input in our input space. So I'll illustrate on a toy example. On the left side, we have an original network, and on the right side, we have the updated network. And the difference between the two is that we took the weights of the original and rounded them to the nearest whole number. And we're interested in proving that the difference in outputs between these two networks is less than 0.1 when x1 and x2 can take values between 0 and 1. So a naive way we can approach the problem is to use an existing verification tool to compute the bounds. Current state-of-the-art tools are based on symbolic interval analysis, so we can use them to propagate symbolic intervals through the network, which will give us a lower and upper bound on the outputs for the networks. So we can do this for both networks, and then subtract the bounds, which will give us a sound overestimation on the difference between the two networks. However, this tends to produce very loose bounds. And the reason why is that after propagating the symbolic intervals through the network, the final output bounds tend to have very significant errors in them. Then when we subtract the bounds, the result is often too loose to be useful. So in contrast to this approach, our approach is to compute the difference in a layer-by-layer fashion instead of waiting until the final output layer to compute the difference. What this means is that we do some of the difference computation before significant errors have accumulated, and this tends to produce much tighter final difference bounds. And like previous work, we base our approach on interval analysis. So the way our approach works is we would start at the first neuron in the first layer, and we would compute the difference in input between the two networks. So for the first neuron, the only incoming edge weight that changed is the incoming weight from x2, which was reduced by 0.1. Since x2 takes values between 0 and 1, the min and the max difference in the input to this neuron is from negative 0.1 to 0. So after we compute this interval, then we must apply the activation function to the interval and widen it if necessary. Then we would move to the next neuron and repeat the process. So for the second neuron in the first layer, the only incoming edge weight that changed is from x2. And since this edge increased by 0.1, the min and the max difference in input to this neuron is 0 to 0.1. So now, after finishing computing the difference intervals for the neurons in the first layer, we could use this result to compute the difference for the subsequent layers. But in this case, we don't have a subsequent layer, so we just propagate them to the output and combine them. And as we can see, the result is typically much more precise. In addition, we also implement a refinement procedure based on partitioning the input space into disjoint subregions. So what this means is that if there exists a proof, ReluDiff can always find it. But of course, this problem is NP-complete, and in the worst case, our algorithm is exponential. But we still find that it's practical for many practical use cases. So this is a very simple overview of ReluDiff. However, the actual algorithm is much more involved, and I'll refer you to the paper for those details. Okay, so now let's look at our evaluation. So we evaluated ReluDiff on 3 popular machine learning benchmarks in the literature. The first is the Akashu family of neural networks for aircraft collision avoidance. And for the other 2, we trained neural networks on the MNIST dataset for image classification and the human activity recognition dataset from UCI. And for all of these properties that we considered, we took the original networks that we trained and rounded their weights from 32 bits to 16 bits. And then we chose an epsilon that would verify that the output does not change by more than plus or minus 5%. And in total, we created 842 properties. So as a comparison point, we took 2 state-of-the-art verification tools, namely ReluVal from Columbia and DeepPoly from ETH Zurich. And we used them in the naive way described in the previous slides. So here in this bar chart, the blue bars represent the number of properties verified by ReluDiff, and the green and the yellow are those by ReluVal and DeepPoly. And to summarize, ReluVal verifies 332 more properties than these tools, and for the properties where both tools finished, ReluDiff is often 2 to 3 orders of magnitude faster. So as a final comparison point, we took a very large MNIST network with 4 layers and 4,096 hidden neurons and rounded the weights to 16 bits like before. And then we took each tool and ran a single interval analysis, so without any refinement, just a single propagation of intervals through the network. And then we measured the epsilon verified. And the table on the right shows the min, max, and average epsilon verified for this problem. So basically the table shows that ReluDiff is up to 66 times more accurate than ReluVal and 12 times more accurate than DeepPoly. So that's everything I have. To wrap up, I just presented ReluDiff to you, which is the first tool targeted at differential verification of neural networks, and in particular the first tool targeted at proving the equivalence of 2 neural networks. So with that, I'll take any questions. Thank you.